Next, we will use a clustering algorithm to identify related groups of stocks within XLK. Now let's discuss two ways you can use this data to help you find pairs. The first thing you can do is run a cluster analysis. What is clustering? It is categorizing. You cluster when you organize your kitchen. You put utensils with other utensils, cookware together, and you stack similar dishes. Clustering is a way you group things. You start by picking some number of clusters, then you will group your objects into these clusters. Within a cluster, you find objects more similar to each other than to those in other groups. To get ready for hierarchical clustering, you select a matrix. The matrix you use is your daily returns matrix. You store each stock's return in a column. You bundle all the columns you want to use in a row. You then form the matrix, which has as many rows as there are observations and as many columns as there are stocks. Once you have a matrix, you select a way to compute distance. You have a variety of ways you can do this. We'll use Euclidean method of calculating distance. The formula is d equals square root of the sum of x minus y quantity squared, where x is the distance of the first point and y is the location of the second point. Note that Euclidean distance is the shortest distance between 2 points. There are other ways to compute distance. We will not explore these. We expect that two stocks that are close in distance will wind up in the same cluster. We call this type of clustering agglomerative clustering. We'll think of it as bottom up. Here's how it works. You would like to start with the two stocks that have the closest distance. This forms a cluster. The companies that are most similar are the first ones to form a group. Then you find the next best group. This will either be another stock that goes in the first cluster, or it can be a new pair that forms a separate cluster. You continue this process of finding the next best cluster. You do this until you are left with just a single cluster. The closer the distance between two companies, the more similar the returns of one company are to those of the other. The more likely they will be in the same cluster. Here you can see that V or Visa and MA, MasterCard, are the first companies to form a group. They have the lowest height value along the y-axis. The next most similar companies are ADP and PayX, both payroll processing companies. They have the second lowest height. Then comes TXN or Texas Instruments and Maxim. Again, this is the closest distance between two stocks. The first three pairings used two stocks that were similar. Now you continue to look for the next best match. It is actually between ACN and the ADP PayX cluster. You use a measure of providing a center for a cluster. ACN's distance to the ADP PayX cluster is closer than any other pairings. This step illustrates the bottom-up approach. Eventually, you will join everything to a cluster. Here's how you can use cluster analysis to eliminate some data. ADP and PayX are very closely related, as seen by their very low height. In fact, it is the lowest. You may choose to drop one of the two stocks to simplify. Based on the fact that ADP has a heavier weighting in the ETF, you may drop PayX. Both are in the same subsector of IT services. However, you can also propose subgroups. Here's the same tree cut into 4 groups. AMD is the only group with just one member. Let's take a look at how this looks when plotted in 2 dimensions. AMD again appears to be in a group of its own. Dimension 1 and 2 represent the 2-dimensional plane contained in 68D hyperspace that minimizes the distance between cluster members and maximizes the distance between clusters. Next, we will run a principal components analysis of the stocks in XLK and create a scree plot. What are principal components? Think of principal components as a data rotation technique. In the plot, we see data for 9 common features of 30 different models of cars. Using principal components analysis, we are able to rotate the 9 feature dimensions and come up with the 2 principal components that explain the greatest amount of the variation between car models. The first principal component explains 63% of the variation, and the second 23%, for a total of 86%. Now we are able to see the similarities and differences between car models in 2-space rather than 9-space. Now let's look at a somewhat more complex plot of the data for the 68 companies in the XLK ETF. Here we see that the principal component 1 accounts for over 50% of the variation and is strictly positive. Principal component 2 accounts for 6.2% of the variation and can be either positive or negative. AMD is again off by itself. These 2 dimensions also have 2 important characteristics. First, the dimensions are uncorrelated. That is, the axes are perpendicular or orthogonal to each other. Second, the dimensions are prioritized such that the first dimension will explain the largest amount of the variation in the data. The second dimension explains the second largest amount of variation. Continuing, the third dimension, not shown, explains the third largest amount of variation and is orthogonal to the first 2. This continues for all dimensions. The good news for you is interpretability. You can interpret these dimensions more easily than the original space. Now let's examine the scree plot for the stocks in XLK. To understand a scree plot, let's first ask, what is a scree? A scree is a gentle slope consisting of small loose stones that have fallen from adjacent cliff faces. You would not want to fall off the cliff into the scree. For a good principal component analysis, the scree plot should have a cliff and a scree. Typically, the cliff is one or sometimes several principal components that explain most of the variation in the data. Component 1 does indeed capture more than half of the variation of the data. Then there is a sharp drop-off. You see this because we chose related stocks. When you consider the stocks in the technology sector, they're going to have a high correlation matrix. This plot also shows how much variance each component explains. On the x-axis, you see each component. On the y-axis, you have variance. This is a good scree plot because you need only a few components to explain most of the variation in the data. Although there are 68 dimensions, let's focus on the first 10. These 10 dimensions contain 87.5% of the variation in the data. In the next session, we will examine how each technology company affects each individual component. This will give you another way of grouping data. This can give you another way to form pairs.